A very good evening to all, respected professors and my dear friends. Today I will be presenting my PhD defense seminar entitled The Development of Nickel Manganese Tin / Gallium based magnetocaloric alloys and alloy polymer composites. This work I have done under the supervision of Professor Jayanta and Professor Debottam in the School of Nanoscience and Technology, IIT Kharagpur. So I have arranged my presentation along these certain lines. Beginning with the introduction and literature review, I will go to my working chapters and then followed by conclusions and then the reply to reviewer comments. The conventional refrigeration, as we all know, is done by the vapor compression cycle, which is an inherently low efficiency process as well as a major contributor to environmental damage. The vapor compression cycle releases many harmful gases in the atmosphere like CFCs and HCFCs, which trigger the formation of ozone holes. Moreover, as India is going towards an advanced economy, more and more cooling is needed, and that inefficient cooling process already acts as a continuous downward spiral where that energy requirement is also more and the creation of damaging gases is also more. International Energy Outlook has suggested that India's residential energy consumption will increase year on year for the next 25 years, and thus some energy efficient cooling processes are of need. The magnetic refrigeration technique based on the magnetocaloric effect has been suggested as a substitute to the conventional vapor compression techniques. Here the magnetocaloric effect is determined as the heating or cooling of a sample as it is magnetized or demagnetized. Magnetocaloric materials are presently subject to interest due to the promise of energy efficient magnetic refrigeration at various temperatures, certainly around room temperature as well as cryogenic temperatures. Here we have a fundamental layout of the processes involving a magnetocaloric material. We see that in the lattice the atoms or the spins are initially disordered, and the total entropy of the material can be expressed as the summation of magnetic entropy, lattice entropy, and electronic entropy. As we can neglect the electronic entropy, the magnetic entropy can be reduced if we quickly magnetize the sample. As we magnetize the sample, the magnetic entropy drops, and correspondingly heat is generated which heats up the sample. The heated up sample can be cooled down by a heat transfer fluid, and as it is back to its normal temperature, if we demagnetize the sample, a net cooling down effect will be there. Thus, if we do this process cyclically, we can achieve some sort of refrigeration via the magnetocaloric effect. If you follow the magnetocaloric effect timeline, initially the magnetocaloric effect was observed or discovered by Warburg in 1981, and then Debye and Geo independently proposed that application for room temperature applications or low temperature applications. Then the 1933, that first time that 1 Kelvin barrier was breached by using paramagnetic salts in a closed cycle refrigerator. Then Pecharsky and G. Schneider of the Ames National Lab developed some interesting magnetocaloric materials showing high magnetocaloric effect, which rendered or made significant research interest, as these materials could be practically employed as a magnetocaloric material in refrigerators. Some essential properties that any sample should have if it wants to be a magnetocaloric material at room temperature is that the critical ordering temperature PC should be in the vicinity of the room temperature. A large magnetization difference should arise out of the first order or a second order phase transformation, and which should drive a large isothermal entropy change. A large adiabatic temperature change should be a resultant out of the demagnetization and magnetization process, and ideally it should have low production costs and should be non-toxic. Some noted families of magnetocaloric alloys have been presented here. Here we see that the magnetocaloric effect, giant magnetocaloric effect being reported by Pecharsky and G. Schneider in 1997, and then Lafayette in 13, which is another popular magnetocaloric family, which has been independently proposed by some researchers from Sendai, Japan. But the disadvantages of these present magnetocaloric alloys are they contain rare earth materials, and these rare earth materials have some availability problems and are of high cost, which motivates the research on some separate items which do not involve rare earth materials. An alternative to the rare earth based alloys are the Husserl alloys. These are magnetic intermetallic alloys, usually possessing the formula X2YZ for the full Husserl type alloys. Alternatively, XYZ can also be formula for the half Husserl alloys. Their magnetism usually results from the double exchange interaction between the manganese atoms. Manganese atoms are present in the lattice. Some notable and well-studied alloy systems are nickel, manganese, indium, tin, gallium. Out of this, we have mainly focused on nickel, manganese, tin, and gallium in our work. out of besides the magnetocaloric effect, these alloys also show some interesting properties such as magnetic field induced strain, elasticaloric effect, magnetic resistance, and vibration damping effects. Here we see the entropy change plots from nickel manganese tin sample showing giant magnetocaloric effect. Here, sample is getting heated up or cooled down as it is progressively loaded or unloaded, and the camera is mapping the change in temperature of the sample. And here we see that example of a magnetic field induced strain. As a magnetic field is applied parallel to the sample axis, or C-axis, that sample changes its direction, and these have interesting applications in many domains. The multifunctional properties, as we had discussed, usually arise from a Martin-City transformation. This Martin-City transformation usually occurs from a cubic high temperature phase to a tetragonal or modulated Martensite phase. The Curie temperature, the magnetization change, and entropy change are all determined by the dynamics of the Martin-City transformation. The the dynamics of the transformation can be tuned and modified by various processing methods such as by refinement using rapid solidification, rolling, or milling, and even also annealing. The processing parameters which have been done on the sample also influences the ground state magnetic properties of the sample. Here we see typical Husserl alloy undergoing two forms of transition. Here we see that as we cool below 350 Kelvin, the first undergoes a second order transition without any hysteresis. Then it undergoes a first order magnetostructural transformation. Usually most of the research works on the Husserl alloys are designed around this magnetostructural transformation, as this involves usually a fast change in magnetization, and thus the associated effects are also more pronounced. Here I have summarized some nickel manganese gallium alloys which have been processed differently and annealed or given different thermomechanical treatments. We see that as we are changing the geometry of the sample, the Martin-City transformation temperature, the magnetization change, and the isothermal entropy change are differing quite significantly. Thus, we can see that there is some scope that by tailoring or applying different processing parameters, we can achieve something new in this sort of Husserl alloys. Based on the literature survey, I have identified 4 problem statements. We see that the evolution of phases, microstructure, and Martin-City transformation in Husserl alloys in suction cast Husserl alloys mostly has not been widely explored. Furthermore, the atomic order in the Husserl alloys, which is a point which can be tuned, can also be modified, and the MCE characteristics and MT characteristics can be studied. Furthermore, multi-element Husserl alloys of this form, which have usually more than 4 elements, can also be investigated by various after processing methods such as lead spinning or suction casting. Moreover, that literature also is less on the magnetocaloric composites. Therefore, we can also try to develop a new class of magnetocaloric composites which can have multifunctional prospects as well. Here is my work plan. I have briefly outlined nickel manganese tin, nickel cobalt manganese tin doped with titanium, and nickel manganese gallium alloys have been fabricated. Nickel manganese tin and titanium doped nickel cobalt manganese tin alloys have been suction cast as well as melt spun, and after that various characterizations have been carried out. For the nickel manganese gallium alloys, we have only prepared ribbons and then ball milled the ribbons and then incorporated into a polysulfone matrix to obtain a multifunctional alloy to see their magnetocaloric effect as well as the vibration damping performance. The experimental and characterization methods are outlined here. As I have said, we have prepared 3 samples. The wheel to surface speed or the melt spinning speed of the samples are outlined here as 19.5 meters per second, 1715 for the 3 systems respectively. Annealing temperatures were decided on the basis of the ordered disordered transformation temperature observed in the Husserl alloys. After the annealing was completed, the samples were either water quenched, air cooled, or furnace cooled. This color coding represents the cooling rate that has been imposed on the sample. Without any processing, the as cast rod or as spun ribbons has been notified by this light blue color. Water quenched samples have been notified by this orange color. The furnace cooled sample has been notified by a green color, and the air cooled samples have been notified by marked by yellow color. The characterization and analysis techniques have been outlined here. Mainly we have performed the regular characterization by XRD, SEM, TEM, PhD, etc. XRD profile fitting was done by MOD. The ab initio calculations was performed by Y2K, and micrograph analysis was carried out by the image software. Here we have the first suction cast rods of nickel manganese steel. We see that the as cast rod has a 3-phase microstructure, which is also shown in the SEM BSc micrograph. Moreover, after annealing, we see that although the L21 phase increases in volume fraction and the DO3 phases decrease, but the small gamma phases do not dissolve completely even after annealing at 1273 Kelvin. It is worthy to note that this DO3 phase and the gamma phase are not non-transforming phases, and they do not impart any magnetic properties to the sample. All the properties that we get is from this L21 phase, and the more the volume fraction of the L21 phase, the better is the functional properties of the sample. Here I present the magnetization as a function of temperature in the as cast and the water quenched rods. We can see that both the samples are showing only a second order magnetic transformation. No first order transformation, which is usually desirable, is not present. We see that the ZFC and FC curves of both the samples are diverging, which show that some magnetic inhomogeneities may be present in the samples. Both show a step-like transition at the blocking temperature TB. The sample, we can also see that the sample contains some predominant magnetic ordering up to 8 Kelvin. Thus, we can say that combined with the divergence in the two curves and the presence of magnetic long-range ordering up to low temperature, we should investigate the ground state properties of the sample. Here I have prepared two unit cells for the ab initio calculations. Here is the stoichiometric nickel manganese tin cell Ni2MnSn, and this unit cell is substituted by the manganese atoms at the regular tin sites, and we have this composition, this unit cell which is corresponding to my composition. Here we have seen for the various results that we have employed also two spin configurations on this unit cell. One is the parallel configuration of spins. The manganese spins are competing or interacting in a parallel manner, and in another case there is some anti-parallel interactions between the manganese spins. We see that the anti-parallel interaction has the lower value of lattice parameter, and although it shows a lower mu, total net moment, it is ferromagnetic. Both the configurations are ferromagnetic, and the APA alignment of the spins is energetically more favorable. That we can also see in the energy landscape, but it is not presented here. Furthermore, if we see the spin density maps, we see the difference density maps recorded for this previous unit cell, that unit cell B for our sample. We see that the main interaction is between the manganese cells, and while the nickel atoms are ferromagnetic in themselves, they are not contributing to much interaction. Thus, we can conclude that the magnetization in the nickel 50 manganese 36 SN14 unit cell results from the manganese atoms in the lattice, and the unit cell can possess a ferromagnetic ground state basis of these calculations. The exchange bias and memory effects were studied in this part. As the samples were showing some divergent ZFC and FC curves, we have first cooled the samples in zero field and then in 0.5 Tesla or 5 kW state field. We see that under zero field cooling there is no shift of the loops. That means that there is no significant exchange bias present in the sample. But whenever we are doing field cooling, there's a loops shift to the left of the axis, which is a characteristic of the conventional exchange bias effects. Calculate the value of the exchange bias effect, and we find that it is 95% at 8 Kelvin, and it diminishes as we are increasing the temperature, which is shown in the figure C. However, also one thing to notice is that the ascending and descending branch of the image loop, which are showing the exchange bias effects, these are not symmetrical. The ascending branch of the loop shifts usually without a corresponding shift in the descending branch, and thus we can think that there is some inhomogeneous states or some glassy states which have complex interactions which are leading to this kind of interactions or image loops in the sample. Thus, the spin glass clusters were tested by the stop and wait protocol in the ZFC. When we were first, this ZFC curve was recorded without any stopping in between, and after that, this stop and wait ZFC was recorded. When we were cooling down the sample, we were stopping here at around 190 Kelvin for 1000 seconds to check the memory effects in the sample. And then when we are recording the curve, we see that there is a dip in this ZFC magnetization, which suggests that there is a memory effects present in the sample. Thus, we can confirm that spin glass clusters are present in the sample, and the exchange bias effects which are arising is a result of the spin glass ferromagnetic spin glass interaction in the sample. But we can also cannot conclude that whether that exchange bias effect is arising from a interfacial effect between the two phases that I had shown before, or a glassy cluster ground state. McHenry and co-workers have suggested that the glassy clusters in a exchange bias showing sample would be correlated with the clocking temperature and magnetic anisotrope energy using this relation. Considering the value of K as taken from a reference, we have obtained an average value of 6.662 nanometer, which seems large considering the unit cell. Therefore, some detailed study may be carried out to investigate the true nature of the spin glasses present in the sample. The magnetocaloric effect has been studied here. We have seen that for the second order transformation, a high isothermal entropy change of 5.98 joules per kg has been observed, and the value of RCP is also correspondingly large. It is around 18.5 joules per kg for field change of 50 kilohertz. The dynamics of the second order transformation has been studied by the critical exponent analysis. Here we can see that the three exponents can describe the sample's second order transformation occurring in a sample as we approach the sample from below the TC. Initially, we have plotted the arrow plot or regular plots for the values of exponent 0.5 and 1. We see that although the lines are parallel to each other, but they are not uniformly straight in the high field region. Therefore, we see that we think that some deviation may be there from the particular values of the main field exponents. Then we have applied the modified arrow plot methods. Using the straight line extrapolations of these isotherms, we find the values of MS, and the log of MS and log of this reduced temperature has been plotted, and spontaneously for above the TC, the log of inverse susceptibility and log of reduced temperature has been plotted. And therefore, we iteratively continue this fitting until this plot becomes fully parallel to each other and the lines become straight in the high field region. Thus we see for the beta value of 0.55 and gamma value of 1.09, the following things have been achieved, and we can say that our sample, the second order transformation in our sample is close to the main field approximation but not entirely following it. Similar results have been obtained when we are plotting by the Covell-Fisher method. We see that the values obtained by the Covell-Fisher method is around 0.58 and 1.05. Which is agreeable to the modified arrow plot method. The TC value is also around 330 Kelvin, which is similar to that we had obtained from the MT plots. When we are plotting this with these values in the universal curve, we see that the M and H, scaled M and scaled H falls into two distinct universal curve, one for above the TC and one for below it. Thus we can say that the calculated exponents are correct within our, or they are consistent within our scope of calculation, and these are the values which have been found out for the sample. Thus, similarly, we can say that long range order is present with some inhomogeneity, which can be due to the presence of multiple phases in the sample. The summary of this chapter is that we have prepared suction cast on annealed rod of nickel manganese tin. The as cast rod revealed the presence of three phases. The electronic structure and spins were studied by ab initio calculations. No MT was observed in either sample. An exchange bias effect and spin glass FM interface, which is generating the exchange bias effect, was observed, and large magnetocaloric effect was also originating from the second order transformation, corresponding with a large refrigeration capacity or relative cooling power. The critical exponents are also studied and are found to be close to the mean field model. In this chapter, I will outline the effect of the post-annealing cooling rate on the MT and the magnetocaloric effect in nickel manganese tin ribbons. So, we have produced nickel manganese tin ribbons. Here we can note that the produced ribbons are of a monophase, which is different from the suction cast rods where three phases were generated. No untransforming phases has been found in the sample, and only a pure austenite L21 has been found. Then the ribbons were annealed at 1173 Kelvin and cooled down by three different paths having a varying cooling rate, which is the furnace cooling, air cooling and water quenching. We see that the atomic order, which is derived from the integration of the superlattice peaks in the four samples, we see that it increases considerably or not much upon furnace cooling and then decreases as we increase the cooling rate. Similarly, we have outlined the lattice parameters obtained by the Rietveld method. We see that the crystallite size, however, do not show a linear trend with the cooling rate, but the atomic order definitely does. Similarly, the microstructure of the ribbons also significantly change as we are changing the cooling rate. The equiax grains which are growing along the TD of the sample, and they now span the whole cross section of the ribbons. But however, the air cooling ribbons also have large grains, but smaller equiax grains were also observed. Here I have outlined the evolution of the microtexture in the sample. Both the aspen ribbons have shown some strong solidification texture. The solidification texture correspondingly weakens upon annealing, and the misorientation angle shifts to a higher value, so that the distribution changes. Furthermore, the pole figure suggests that there is a strong fiber texture being developed after melt spinning, and this fiber texture weakens upon annealing. The microstructure and atomic order has also been tried to correlated by electron microscopy. We see that for the aspen ribbons, we see long equiax or columnar grains, as we were seeing in the cross-sectional images. For the furnace cool sample, these have definite grain growth, and when we are taking a dark field image from the 111 spot of the diffraction pattern, we see that the ordered L2 and ordered domains light up, and we see that a considerably large domain of approximately 2 nanometers has been found in the furnace cooled sample. And the corresponding the water cooled sample also shows a martensitic domain within the prior austenite grain, and this martensitic domain is having a modulator structure, which is the 4O modulator structure, which we can verify by the presence of the 3 satellite reflections in this image. Therefore, we see that the TM studies confirm that the atomic order definitely increases after furnace cooling. The transition temperature also show a strong relation with the atomic order. Here we see that the martensitic transformation temperature initially was around 280 Kelvin, which reduces considerably after furnace cooling to around 186 Kelvin, and it is highest in the fast cooled samples, which is higher than the as-cast ribbons. Similarly, the Curie temperature of the austenite also TC, this also changes as the magnetic correlations are varied with the atomic order. Here we see that the around from 310 to 302 it is going, that magnetic correlations is getting weakened as the atomic order is going from high to low for these samples. The decrease of the this martensitic transformation temperature can be determined or can be explained by the increase or decrease of the free energy of the FM austenite. As the free energy of the FM austenite is decreasing, it is stable across a larger transition temperature, and thus the transition temperature is being pushed down to a much lower level. A similar story is being shown by the magnetizations as a function of temperature, but we see that there are multiple transformation temperatures present in all the samples. The aspen ribbons and the air-cooled ribbons and water-quenched ribbons have a hump-like transformation, but this furnace cooled ribbons have a very smooth and sharp first-order transformation corresponding and a wide second-order transformation. We see that there are multiple ordering temperatures also, and the nature of the samples at each point in this transition is also not very clear. To see this, we have performed image loops at the temperature range of 200 to around 300 Kelvin for the water quench sample. We see that the loops are in this region are not saturating and have a very low value of coercivity. These are not very similar to what we see for ferromagnetic samples, and we can say that there is some transitory paramagnetic or superparamagnetic behavior after the empty, but that has been probed or determined by AC susceptibility studies. The low temperature magnetic properties also show a big bifurcation between the lines for all the samples. We see that for both the samples or for all the samples, TP has been observed, but for the unspooled sample there is no characteristic TP, and only a step-like transition has been observed. No peak has been observed. These are also peaks due to the relaxation or the freezing of magnetic clusters as we are cooling down the sample. The characteristics or the glassy characteristics in the sample has been calculated by the or probed by the AC susceptibility studies. Here we have used this equation which calculates the value of the empirical parameter, and the empirical parameter has been calculated to be around 0.008 and 0.001 for the samples. We can say that this parameter is much higher than the superparamagnetic values or for spin glass values, then we can say that these samples are neither in those categories. Thus, previous studies have suggested that for some alloys which have a varying chemical or atomic order, these values are reported when some small FM clusters develop in the sample. These FM clusters can have a strong dependence on magnetization, and these FM clusters show a MH loop sort of similar to paramagnetic materials, superparamagnetic materials. And thus we say that the development of FM clusters in the AFM matrix has happened post the transformation in the first order transformation in the samples. The magnetocaloric effect of the samples has been shown here. We see that after furnace cooling, the refrigeration capacity of the samples is increasing, and although the value of the isothermal entropy change is decreasing, the values of the refrigeration capacity is increasing, and thus we can say that the furnace cooling after annealing is an easy way to increase the refrigeration capacity or magnetocaloric properties of an alloy. In this chapter, thus we have prepared ribbons which are monophase ribbons and then annealed and cooled down by 3 parts. We have related the atomic order with the Mantle-Citic transformation. We have related the atomic order with the ground state magnetic properties, and we found that the ground state nature of the samples was predominantly FM clusters in an AFM matrix. Furthermore, slow cooling also increased the relative cooling power of the sample compared to that of the aspun ribbons. In this chapter, we will discuss the effect of processing route and Mantle-Citic on the annealing on the Mantle-Citic transformation in multi-element titanium dope nickel cobalt manganese tin alloys. Here I have laid out the XRD plots for the as-cast rod and the annealed rod and for the ribbons. We see that similar to the nickel manganese tin systems, during sample casting 3 phases are being developed, whereas it is not the case when we are doing rapid solidification. The 3 phases are the L21 B2 austenite. The L21 austenite is present in the as-cast rod, but after annealing it goes away and only B2 austenite is present. DO3 phase and disordered gamma phase are all there, and it cannot be dissolved by annealing. Moreover, the lattice parameters of the samples have been also denoted. We see that upon annealing, the lattice parameter of the ribbons increases slightly, which has a different implication as we will discuss later. Here I have shown the SEM images of the microstructure of the ribbon of the as-cast rods, annealed rods, and the ribbons. We see that the 3 phases are distinctly present. After annealing, the gamma phase is persisting, whereas there is no such case in the ribbons, and we can say that the belt spinning is a beneficial way to fabricate the ribbons, which has a single phase structure and the untransforming phases are low in number. Furthermore, the PhD IPM map shows that the solidification texture has been developed in the sample after rapid solidification. The solidification texture has been studied by these pole figures. We see that for the aspun ribbons there is an intense solidification texture along the MD, and this reduces upon annealing in the annealed ribbons. Furthermore, annealing also develops some other textures apart from the fiber textures, such as 200, 843 and other textures as well. TEM bright field images show that the grain growth, while it has observed, some new microstructure has been developed in the samples after water quenching. This microstructure is sort of a tweed morphology, and this can be assigned to the presence of strain glass cluster. This strain glass cluster usually increases the lattice parameter of the sample, which we have seen in the XRD plots. And this and the development of strain glass phases usually has shown to arrest the Mantle-Citic transformation in these alloys. What we had discussed, we are seeing here in the while annealing the as-cast rods, the transformation is not getting reduced or suppressed. When we are annealing the aspun ribbons, the strong transformation present in the ribbons is getting quite some suppression, and it does not proceed even if we are doing field cooling with a 3 Tesla field, external field. We see that the austenitic phase is being maintained till low temperature when we are doing field cooling and then taking MH loop at around 10 Kelvin. We see that the austenite is being present in the sample. The similar story is being presented by the DSC curve, whereas the strong transformation is present in the aspun ribbon. There is no such traceability transformation, and only 3 small relaxation peaks are present which is corresponding to the relaxation and freezing of the strained glass clusters. The preferred orientation which had developed of the texture which has been developed in the sample were also correlated with the magnetic properties. Here we had prepared a sample, and the rolling direction of the samples was subject to different angles of the magnetic field. Initially the magnetic field was parallel to the sample's rolling direction of the solidification direction, and then gradually it was taken to 90 degrees. Here we can see that definitely as we are rotating the sample in the magnetic field, there is some definite dependence of the magnetization with the texture. We see that the saturation magnetization as well as the spontaneous magnetization is highest when the sample rolling direction is parallel to the RD, and it gradually decreases as it becomes perpendicular. Bunge had stated that the saturation magnetization behavior of any sample can be described by the crystallographic texture, whereas the spontaneous magnetization of the sublattice magnetization is usually related by the magnetic texture inside the samples. Corresponding to the PhD IPF maps, we see that as the spontaneous magnetization is decreasing as we are keeping the sample perpendicular to the magnetic field, 001 direction of the unit cell must be the harder magnetization direction of the unit cells. But more the information can be only found out by plotting the magnetic pole figures. Magnetocaloric effect of this sample has been studied here. We see that the sample as cast ribbons shows strong dependence with the magnetic field, and also a field-induced transformation at around 2.5 Tesla. We can also see that the values of the calculated maximum entropy change is quite high, 16.59 joule per kg Kelvin for an external field of 50 kW strength, as well as we have calculated by the Clausius-Capron equation, which has come out to be around 12.6 joule per kg Kelvin. The maximum adiabatic temperature change of the sample has been around minus 2.6 Kelvin, which has been achieved under a field change of 20 kW. Here I will show a video which describes the the adiabatic temperature change as the sample is magnetized or demagnetized. We see that as we are inserting or drawing out the sample from the magnetic field, the temperature is changing very quickly. First, the sample is maintained around the TC. First, the sample is maintained around its TC, and then it is magnetized. However, when we are going above the TC and doing a similar process, there is no temperature change in the sample, as we will see now. The temperature is only increasing corresponding to the ambient temperature. Thus, we can say that the magnetocaloric effect can be observed in the sample. So, in this chapter, we have fabricated multi-element nickel, titanium, cobalt, manganese tin samples, and prepared the suction cast rod and the melt spun ribbons. The annealing treatments were carried out. The annealed ribbons did not show any good magnetotic transformation, but only showed a suppressed transformation, which was related to the growth of strained glass clusters in the sample. Very excellent magnetocaloric properties in the sample was shown, which corresponded to a high delta T adiabatic of around 2.6 Kelvin for a relatively small field change of 20 kW. In this chapter, I have outlined the fabrication of a multifunctional composite material. Here, I have initially fabricated a nickel manganese gallium ingot and then melt spun to form ribbons. Though we see that the nickel manganese gallium ingots initially possessed a tetragonal non-modulated martensitic structure, which transforms into a modulated martensitic structure upon melt spinning. And this martensitic structure is retained after annealing and furnace cooling. Furthermore, we need this 7M martensitic structure in the samples because initially this non-modulated structure does not have many mobile twin variants. To obtain our goal of a vibration damping composite, we should fabricate samples having a 7M modulated structure. Thus, they were melt spun to form ribbons. Then the ribbons were milled to form ball milled particles, which had a size distribution of around 16 micron. These particles were then incorporated into a polysulfone matrix by solution casting to obtain a composite and here is the physical photograph of that composite, which is quite thin and flexible in itself. So here is the X-ray diffraction and phase analysis. We see that we are having obtaining XRD patterns which are corresponding to a 7M modulator structure. Besides the primary reflection, many satellite points are also being observed, which is highlighted in this inset. And here is the characteristic unit cell of a 7M modulator structure. The 7M modulator structure have a space group, primitive space group of P2M, and whereas the non-modulator structure have an I4MMM space group. The lattice parameters have been extracted by read-mill refinement and summarized here. Basically the modulated Martin-Selick structure also has a definite displacement of the atoms from the respective lattice positions, which is following a modulation vector, or as which is suggested as Q. The 7M modulated structure usually contains a lot of mobile twin variants, and these have been shown in the next slide. Here we see the development of a modulated twin variants in the nickel manganese gallium system. Initially, when the austenite transforms into martensite, the non-modulated martensite forms, and these tetragonal unit cells are the first building blocks of the non-modulated martensite. Initially, there is no specific repetition in this arrangement, and after further cooling down, the 7M martensite forms. These 7M martensites have an alternating twin boundary, which have characterized by a long and short period. The long period is equal to 5 and the short period is equal to 2. Therefore, that 7th unit keeps on replicating as we go up and down this scale. Here also we see that this HRT images show a austenite cubic besides the modulated martensite phase, and these martensite phases, these small nanotwin phases coalesce to form mesoscale twin boundaries, which are next hierarchy level of the nanotwin boundaries. These are represented by the images here. Both these twin boundaries are mobile, and they can be modulated by external stress fields or by magnetic fields. The structural magnetic phase transformation of the ribbons and the powders has been shown here. We see that there is a strong martensite transformation in the ribbons, which decreases upon ball milling due to the decrease in the magnetic correlations after that deformation in the sample, which is occurred during ball milling. That TC also reduces for the sample. Initially it is very high at around 400 Kelvin for that as measured ingot, and reduces as we develop ribbons and powders. The effect of ball milling has been also present in the magnetic correlations. We saw that the Curie temperature of the ball mill powders also decreased by 4 Kelvin compared to the aspen ribbons. It can be attributed to the weakening of the ferromagnetic correlations as some damage is or crystal deformation is incurred during milling. The nature of the error plots also signify that some deformation or some change is there. The slope of the error plot changes, which suggests that after milling, that second order transition becomes predominant over the first order transformation. The composites also show good magnetic properties corresponding to a magnetostructural transformation and good soft magnetic properties as shown by this MHU. The magnetocaloric property of the composite is also shown here. The highest value is obtained by the aspen ribbons, and then it decreases as the magnetic correlations itself decrease. The magnetocaloric properties also decrease for the samples. The delta Sm has been calculated as 2.85 for the ribbons, and then decreases to around 1, and then further decreases for the composite samples. So this value, although it is detectable in itself, it is not that high, and we should strive for our increment in this by increasing filler loadings or by incorporating a different higher property magnetocaloric material. The thermomechanical testing plots have been shown here. We see that for the storage modulation and time delta plots, two peaks are present in the time delta plot. One is corresponding to the structural transformation of the fillers, and this is due to the glass transition temperature in the polysulfone matrix. So we also see that due to this combination, the glass transition and magnetostructural transformation can be effectively utilized to obtain broadband damping effects in the sample, and these effects can also be shown when we are doing that vibration damping test in a shearing mode, and this is performed in a tensile mode. You can see that in both the cases of testing, these broadband damping effects can be detected in the sample. In summarizing, we produced nickel manganese gallium ribbons which were milled to obtain micron size powders which had an irregular morphology. Multifunctional composite was also prepared by incorporating the matrix into a incorporating the powders into a polysulfide matrix. These composites showed good and concurrent magnetocaloric effects and vibration damping properties. The conclusions of my working chapters are as follows. For the first working chapter, we have fabricated nickel manganese tin suction cast rods. When we see that the anti-parallel alignment of the spins was more favorable compared to the parallel alignment. Furthermore, the as-cast rods produce three phases, which is not that desirable in case of a transforming alloy. The exchange bias effects were also observed in the ACR as-cast rods, which could be attributed to the interfacial couplings between the spin glass and ferromagnetic clusters. A memory effect during the DC magnetization confirmed the presence of these spin glass clusters. Second order transition was primarily observed in the obstinate phase of both the sample, and for the ACR we obtained a large magnetocaloric effect and large electric cooling power for the samples for a field change of around 50 kHz. Furthermore, the critical component exponents associated with the second order transformation were also calculated, which suggested near mean field and long range interactions in the sample are present. The cooling rate, the variation of the atomic order post the cooling rate also was performed by changing the cooling rate of the samples, and the following conclusions could be seen that the melt spinning produced monophase ribbons compared to the three-phase microstructure obtained in the as-cast rods. Isothermal holding for an extended period created uniform microstructures and uniform crystallite sizes, but the functional properties of the samples was modulated by the atomic order, which was dependent upon the cooling rate. There existed multiple ordering and spin freezing temperatures in the sample, which suggests that there is a lot of complex magnetic interactions in the annealed and aspen ribbons. We see that the ground state order of the samples was primarily ferromagnetic clusters in the backdrop of long range antiferromagnetic state. Furthermore, furnace cooling increased the working region of the ribbons, and therefore we can say that slow cooling after annealing is an easy route to increase the magnetocaloric properties of these usual alloy ribbons without using other complex processing routes. In the next chapter, we have studied the effects of annealing and suction casting and melt spinning on the multi-element usual alloys. We see that similar to the case of nickel manganese tin, suction casting here also generates a three-phase structure, whereas melt spinning generates a monophase structure, which is very beneficial for magnetocaloric applications. These monophase ribbons were having a strong, intense solidification texture component of 100 parallel ND. However, annealing the ribbons generated some stained glass clusters, which stopped or suppressed the martensitic transformation in the sample, and as well as the aspen ribbon showed a high magnetocaloric effects and RCP and delta T adiabatic change for a low cooling field, which is promising candidate for future solid state refrigeration applications. In this final chapter, I had showed the fabrication of a composite sample incorporating nickel manganese gallium powders into a polysulfide matrix. The flaky powders were incorporated into the sample. Both the samples and the ribbons had mobile twin boundaries. The mobile twin boundaries enabled the application of the sample as a vibration damping applications, and moreover that composites also showed delta SP, which is suggesting of a magnetocaloric effect present in the sample, and the synergistic effects of the structural and transition can be thus employed for both multifunctional applications. Here are the contributions of my thesis. As I was saying, that multi-element Hussler alloy ribbons had shown very good adiabatic temperature change and magnetocaloric effect for a low field change, which we have reported in our work. Also, we have seen that the ground state magnetic properties and the refrigeration capacity can be tuned easily by the cooling rate, and which may be useful in fabricating future magnetocaloric materials of maybe Hussler alloys or other families. composite material was robust composite material was also demonstrated, which is capable of multifunctional applications. In the case of future work, we can see that we can try out the annealing at different temperatures and cooling down at different rates from either above or below the ordered disordered transformation temperature, and as well as we can also study the effect of plastic deformation or other pre-strain on the MT characteristics and the MC characteristics of multi-element alloys. Furthermore, more robust composite having higher volume fraction of fillers and having some thermally conductive fillers can be performed as an extension to the already fabricated nickel manganese gallium polysulfone composites. Here are some of my selected references, and these are the publications. All my working chapters have been published in peer-reviewed journals and in conferences and workshops.
Hey, all of it.
No.
All of it. In front of all of you. Please. Come. That's formal announcement of it. Come, Debottam.
So maybe we can move the camera to other side.
Interact with the
Got it.
Come.
Camera to the
President, the candidate is out here.
Yeah, sorry. Congratulations, Doctor.
Thank you.
Wish you a great success in your life.
Actually, the most interesting thing is that Debottam, he's not a metallurgist, but he's his undergraduate degree is from electronics.
Electronics. Oh, that is nice actually.
Yeah, that is nice. At the end, we find it is very nice. So at least throughout last 5 years, he has to learn metallurgy, martensite, and all the
Transformation.
let's say and I hope that he has justified that properly.
Yeah, I think you should utilize your background for development of the device,
Yes.
Correct. Absolutely.
and which is not very difficult, I think. Okay, thank you.
Okay, thank you, Professor. We'll see you sometimes.
Okay,
Okay, thank you very much.
thank you very much. Thank you.